Consider the environment around you while watching this video. I doubt that it is absolutely quiet. Most likely, you can hear distractions, perhaps a TV, music, the voice of your favorite magtataho. Yet despite these distractions, you can remain, well, mostly focused on what you're watching. The huge amount of sensory input that everyone is constantly receiving would be overwhelming if humans weren't able to block out some of it. The psychological mechanism of this filtering and focusing ability is attention. Attention acts as a spotlight, a focusing device to bring to mind a particular stimulus. It also acts as a filter blocking out distractions. In this video, we will describe the key features of what attracts attention, what doesn't attract attention even when it probably should, and how attention helps you search for things. We also discuss how to control attention, the mechanics of involuntary attention, and some clinical disorders of attention. Understanding attention is essential in many areas of life. One group that relies on it to make a living are magicians. In 2008, the prestigious journal Nature Reviews Neuroscience published an article by a number of, get this, magicians, explaining how they use knowledge of human cognition to execute their tricks and how this knowledge can help cognitive psychologists understand how the brain works. One sure common skill is what they call as misdirection, guiding the audience attention away from the real trick. Misdirection involves several aspects of attention that we will define and discuss in this section. That is priming, where seeing one object or word or the cue speeds up the processing of a second object or word. And then we have inattentional blindness, where people don't spot or attend to something visually. And then we are going to talk about visual search, where people have to search the environment, the visual environment, for a particular object. So, priming is a phenomenon whereby exposure to one stimulus influences a response to a subsequent stimulus without conscious guidance or intention. The simplest explanation of priming is that the presentation of something, an object or word, makes it easier for the brain to activate its stored representation for that something, word, or object. So if you hear the word square, you are quicker to respond to a square when you see it. Expectations can also be used for priming. American psychologist Michael Posner developed a test called the Posner cueing task, which measures how the attention system responds to different cues. Participants are presented with a fixation cross, an actual cross, or in this example, an arrow in the middle or X mark in the middle of the screen. Then a cue appears directing their attention to one or the other side of the fixation cross. A target appears and participants have to respond to that target. For example, by saying what shape it is. The cue can be valid or invalid. On valid trials, the cue predicts the location of the target. On invalid trials, the cue does not predict the location of the target. Neutral trials in which no cue exists are also used. Now, the number of valid and neutral trials is always greater than invalid trials. So, the participants can expect that the cue is going to predict the target location. The results are that valid cues speed up identification of the target, whereby invalid cues slow it down. Now, people's desires can also prime their attention. For example, alcoholics spot alcohol related objects in a visual scene quicker than non alcoholics. Inattentional blindness is a phenomenon in which people fail to notice or attend to something in their visual world. In 1998, psychologists Erin Mack and Irvin Rock carried out research showing that people can miss something right before their eyes when their attention is distracted. Participants were presented with cross shapes and had to identify whether the horizontal bar was longer than the vertical bar. The crosses were on screen for only 200 milliseconds. Participants were looking at a fixation cross, not looking directly at the not looking directly at the cross shape. People were highly accurate at this task. But when researchers replaced the fixation point with a sharp, with a shape, let's say a triangle, rectangle, or cross, 86% of participants did not notice the change. Now, change blindness is a related and more intriguing phenomenon. People often fail to notice changes that, or rather to an image that seem really obvious when pointed out to them. Normally, when something moves or changes in front of people, the change grabs their attention because it changes their retina, creating uh, transient cell responses to something new. Change blindness and inattentional blindness often occur in films with people missing continuity errors or ignoring a camera operator in the shot. Scientific studies of continuity errors show that 90% of people fail to notice them even if they expect some changes. Change blindness may also be a reason for the type of road accident in which a driver pulls out into the path of another vehicle because he looked but failed to see. Now, in this video, we are to see the monkey business illusion. This video was done by Dan Simmons, and your task is to count how many times the players wearing white passes the ball. Correct number is 16, but did you see the gorilla? For people who haven't seen or heard about the video like this before, about half missed the gorilla. If you knew about the gorilla, you probably saw it. But did you notice the curtain changing color and the player on the black team leaving the game? So let's rewind and watch it again. So there goes the gorilla and and the player wearing black leaving the game, and the curtain changing color. The key here is that when you are looking for a gorilla, you often miss other unexpected event, and that is what Daniel Simon calls the monkey business illusion. All right, so uh, Daniel Simmons offers or offered this explanation for change blindness. First, your brain overwrites the first image with the second, and then after your brain stores the first image, you ignore the next one. Also, you don't remember either image for long enough to compare them, or your brain stores both images but you don't consciously compare them. Also, you don't expect changes, so your brain combines the two images mentally. Another explanation is based on inhibition of return, in which is where you don't look back at somewhere you've recently observed. Inhibition of return prevents you from getting stuck looking at one part of an image. Change blindness typically occurs only for less central aspects of the visual scene and only for things that you don't expect to change. Say, the gorilla or the color of the curtain in this example. So part of the attention system's role is to prepare you for what's likely to change. But the result is that it may not provide you with a true representation of the world. Now, the popular Where's Waldo books or Where's Wally in the UK involves trying to find the eponymous hero in a distinctive outfit in a cluttered scene. There's our hero. So, the task is difficult because the scene contains a lot of other people and objects. And many of them share colors and features similar to the target. Uh, Here's an example of one page in a Where is Waldo book. And since we don't have much time here, let me just point out where he is in this picture. There is our hero. So, now, cognitive psychologists use more formal versions of the task called the visual search task to understand the role of attention in vision. In the visual search task, people are shown an image full of different shapes and they have to say whether a particular shape, called the target, is present or absent. The researcher records the time taken for the participants to decide whether the target is present or absent. So I want you to find the letter B in both figures A, or in both squares in figure A, and O in figure B. So in both displays in A, the B shares, or the letter B shares the same features, vertical and curved lines, as the distractor's letter P. So it does not pop out. You have to check each item in turn, searching for the specific conjunction of features, so you take longer to find the target in the top image because of more distractors. In figure B, the O, or the letter O, is the only shape containing curved lines, so it pops out, and the number of distractors has little effect. So by varying the number of other objects, that is distractors, and the similarity between the target and the distractors, psychologists can discover some interesting facts about visual search and attention. First, if the target is different from all the distractors in terms of a single simple feature such as color or shape, as in the letter O in figure B, it tends to pop out, and the time taken to find the target stays the same when researchers increase the number of distractors. But to report that the target is absent takes longer, and this time period increases with the number of distractors. In a conjunction search, searching for a target that shares elements with distracting items, the target doesn't have a unique single feature, but a unique combination of features. Here, the time to find a present target increases with each distractors added. And deciding that the target is absent takes about twice as long. Now, according to psychologist Anne Treisman's feature integration theory, attention is the glue that binds the features together in visual search. In pre-attentive search, your visual system picks out features such as color, shapes, size, and movements. At this stage, if the target is the only item containing a certain feature, it pops out. But But if the target depends on a conjunction of features, it doesn't pop out and you have to look for it, one item at a time. By attending to an object, you're able to glue the different features together. Pre-attentive search only allows you to process simple features, but it's fast and everyone processes all the features at the same time in a parallel search. To use attention, you need to examine each object one at a time in which is called a serial search, which is slower because you have to attend to each item in turn. On average, people have to examine about half the objects in a display before finding the target. But in order to say that the target is absent, they need to search exhaustively every item. Which is why people take about twice as long to respond when the object is not present. Now, implicit in the definition of attention is the idea that you can take control of your conscious experience. Attention shines like a spotlight on a stimulus or stimuli. It raises awareness of key parts of the things you're attending to while dimming others. It selects what reaches your consciousness. Imagine, for example, that you are studying for a cognitive psychology exam. You are watching this lesson, of course, and writing down notes. While the TV is on, your favorite magtataho is outside hollering about his delectable products, and you're expecting a messenger notification. Now, attention removes the distractions and focuses on the key task, studying, or tasks, reviewing, and listening to the news on TV. In this part of the lesson, we cover how you choose or not what you attend to. We also describe what happens when you have multiple things to attend to at once and how difficult it is. Plus, we explore what factors pushes your attentional capacity to the limit. So, the first thing your brain needs to do when studying is to select the relevant things to attend to. In other words, on what to put the attentional spotlight or unidirectional microphone for sounds. Here, we look at how the brain selects information to attend to. Classic studies of auditory attention use a shadowing paradigm, an experimental task in which participants must pay attention to sounds in one ear but ignore the other. Participants wear headphones and their task is to repeat what they hear. Simple, you say, but psychologists makes things harder by presenting different messages to each ear called the dichotic listening task. For example, the message 1, 2, 3 to one ear and 4, 5, 6 to the other ear. When asked to repeat what they hear, participants report hearing 1, 2, 3, 4, 5, 6. In other dichotic listening tasks, participants have to shadow one ear but ignore the other. They're then asked to recall information from the attending ear in which the message was shadowed, and the unattended ear, the one they were supposed to ignore. Participants are nearly perfect at remembering information from the attended ear, but remember very little from the unattended ear. In fact, participants don't notice whether the language used in the unattended ear swaps from English to German, or even in the same word, or even if the same word is repeated several dozen times. Participants, however, do notice if the gender of the speaker in the unattended ear changes. Furthermore, most participants are unaware of an instruction to stop the task in the unattended ear unless it's preceded by their name. Colin Sherry, a British cognitive psychologist, described this tendency as the cocktail party effect. Even if you're attending to something, you sometimes hear your name spoken. To explain why people don't notice things even when they're in plain sight, or in this case sound, Donald Broadbent, a British psychologist, proposed a filter theory of attention in 1950s. His early selection theory was based on the idea that attention acts as a filter shortly after the senses detect stimulus. Low-level stimulus properties such as volume or pitch are then used to decide what's to be allowed through the filter. Basically, all unwanted sensory stimulation is sieved out. You can see Broadbent's model here, labeled as selection theory. So in this example, you'll see that uh, as a filter, or attention serves as a filter to select to see the selection on the basis of physical characteristics only. So, some researchers use the cocktail party effect to criticize the early selection theory. Specifically, one study criticizes the theory by giving mild electric shocks to participants every time a particular word was presented in the unattended ear. This formed a classical conditioning pairing of a word and a shock. When asked to recall the words, participants couldn't recall the word paired with the shock, but when shown the word, they had a higher skin galvanic response. Their hands got a little sweatier, suggesting that they were mildly afraid of the word. This suggests that they had attended to and memorized the word, but not consciously. Um, Anne Treisman developed the attenuation model, in which attention simply reduces the amount of information that can get through the filter. The early filter still blocks out unwanted stimulation but allows information through that has certain physical properties. Diana Dutch, a British American perceptual and cognitive psychologist, went further and suggested that all information is processed and attention simply filters out the unwanted information and the semantic meaning level known as late selection. So, which is more accurate? Broadbent's early selection or late selection? Experiments show that during highly demanding tasks, people filter out unwanted information as early as possible. For example, when driving along and having a conversation, the talking stops when you reach a busy junction. The, atten- 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 the attentional filter prevents distractions for a more demanding task. During easier tasks, however, you can employ late selection. No doubt you've tried multitasking. That is, deliberately focusing on two tasks at the same time. Perhaps having a conversation with someone while washing up, or having a conversation while driving. How well can you perform the task? What about when you're writing an essay and your roommate or brother or sister who lives with you ask what you want for dinner? How do you swap from the first task to the second, known as task switching? Many people finish the sentence they're writing before answering the question. Now, both multitasking and task switching are examples of divided attention. Recent estimates are that you can lose up to 40% of your productivity if you multitask. In an experiment on multitasking, participants shadowed one list of words from one ear while ignoring a second list presented verbally or visually. The conditions for list 1 and list 2 were respectively spoken words, and then spoken words, or spoken words and visual words. Researchers tested recall for both lists, and accuracy was higher for the spoken words and visual words condition than when the lists were matched across senses. The message is clear. You can divide attention across multiple tasks as long as they're dissimilar enough. One suggestion for when tasks may interfere with each other stems from the working memory model of memory processed by Alan Baddeley and Graham Hitch in 1976, which contains components of processing visual and verbal material. These two components can process information in isolation. A central executive, the control part of working memory, controls the processing in the two components. Task interferes with each other only if they're using the same component of working memory or when they're too difficult. In task switching, researchers have assumed that you have to wait to start the second task until you finish the first. But an experiment in which participants are presented with two tasks concurrently highlights that this isn't entirely true. The first task is to identify whether a sound is high pitch or low pitch by saying high or low. The second task is to identify the spatial location of a square, either left or right, by pressing the appropriate computer keyboard button. If you have to complete the first task before starting the second, the total time to do both tasks should be equal to the time taken to do task 1 plus the time taken to do task 2. However, the study found that the total time to do both tasks in this way is actually less. Nevertheless, reaction time to the second task is longer when following the first task than if the second task is presented alone. Now, the explanation for this effect is the response selection bottleneck model as seen in this figure. The idea is simple. You can't think about how to respond to a particular task until you complete the response to the previous task. This model explains several other effects. You can vary the duration between the start of the first task and the start of the second task, known as the stimulus onset asynchrony, or SOA for short, and it does not affect the overall time to react, provided that the SOA only lasts as long as the processing and thinking time for task 1, known as the psychological refractory period. The logic is that the response has to be initiated for the first task before the decision-making process can begin for the second task. Now, there has been a lot of research on task switching, and here's what we know from the research. It takes more time to get tasks completed if you switch between them than if you do them one at a time. Second, you make more errors when you switch than if you do one task at a time. If the tasks are complex, then these time and error penalties increase. Each task switch might waste only 1/10 of a second, but if you do a lot of switching in a day, it can add up a loss of 40% of your productivity. Task switching involves several parts of your brain. Brain scans during task switching shows activity in four major areas. The prefrontal cortex is involved in shifting and focusing your attention and selecting which task to do when. The posterior parietal lobe activates rules for each task you switch to, and the anterior cingulate gyrus monitors errors, and the premotor cortex is preparing for you to move in some way. I know it's popular to think that you are multitasking, but research is clear that people actually can't multitask, with one specific exception. And I'll get to that in a minute. One thing at a time is that what for many years, the psychology research has shown that people can only attend to one task at a time. Let me be more specific. The research show that people can attend to only one cognitive task at a time, can only be thinking about one thing at a time. You can only be conducting one mental activity at a time. So you can be talking or you can be reading. You can be reading or you can be typing. You can be listening or you can be reading one thing at a time. So we are pretty good at switching back and forth quickly. So we think that we are actually multitasking, but in reality, we are not. So the one exception that I was mentioning earlier is that research has uncovered that if you are doing a physical task that you have done very often and you are very good at it, then you can do that physical task while you are doing a mental task. So if you are an adult and you have learned to walk, then you can walk and talk at the same time. So even this doesn't work very well though. In a study by Hyman and company in 2009, people talking on their cell phones while walking ran into people more often and did not notice what was going on around them. The researchers had someone in a clown suit riding a unicycle. Now, the people talking on their cell phones were much less likely to notice or remember the clown. Um, but young people can multitask, right? Well, if you think that only older people, if you think that it's only older people that can't multitask, you have to think again. A study at Stanford University demonstrates that multitasking does not work even with college students. Clifford Nass's study found that when people are asked to deal with multiple streams of information, they can't pay attention to them. They can't remember as well and don't switch as well as they thought they would, even for college students. So, the next time that you plan to multitask, you have to think again. Now, your attention can be under voluntary control, such as when you decide to ignore your ringing cell phone to carry out watching your favorite TV program. But your attention can also be automatic. Everyone has experienced their attention being drawn to something because of a loud noise or an unusual display. Sometimes, people simply work on what we call as autopilot. Several aircraft pilots have landed aircraft having apparently forgotten to deploy the landing gear, leading the plane to crash land. In many of these cases, the pilots simply went through the landing checklist on autopilot without paying attention. Now, psychologists have used a number of tools to investigate why this happens. Now, in this section, we will cover what factors can interfere with attention and make it worse. We will also examine the important effects of practice has on attention. So, automatic processing can adversely affect your attention. I want you to count how many times the letter F appears in this sentence. So, the most common answer is 3, but the correct answer is actually 6. Many people seem to miss the F's when they occur in the word off. Words such as off, the, and to play a functional role in our language and appear in most texts. They tend to occur much more often than the content words. So, people are more used to them and more practiced to reading them, which means that they're more likely to ignore them. Like anything they have practiced a lot, reading functional words become automatic. The Stroop effect, named after John Stroop, the American psychologist who discovered it, is known as the gold standard of automatic processing. The effect is simple. Participants are presented with a series of color words. For example, green, the word may be printed in the same color as what the word means, which is called the congruent condition as seen in this in condition A in this figure. For example, the word green is printed in green ink or in a different color from its meaning, which is an incongruent condition as seen in condition B. For example, the word green is printed in red ink. Participants have to name the color the word is printed in. So, participants find the incongruent condition much harder and take longer to name the color than with the congruent condition. Reading is so automatic that psychologists assume that the word's meaning disrupts people's ability to name the color. So, the Simon effect is a similar example of automatic processing. Participants are presented with a display in which a symbol is on the left or the right side of the screen. They have to press a left button for one particular cue, for example, the at sign on your keyboard, and a right button for a different cue, for example, the let's say plus sign on your keyboard. If the at sign appears on the left, the trial is considered to be congruent. Whereas if it appears on the right, it's considered incongruent, and vice versa for the plus sign. Participants' reaction time to state that the symbol is present takes longer for the incongruent task than the congruent task, confirming that knowledge of spatial position can interfere with attention. So, lastly, attention is crucial for human survival. Yet, neuropsychological conditions exist in which the ability to attend is severely impaired. In this section of the lesson, we are to look at two attention disorders: spatial neglect and attention deficit hyperactive disorder. Spatial neglect is a relatively common disorder of attention, usually caused by damage to the right parietal lobe. A bit of this is a bit of the brain towards the side and back of your head. Now, patients suffering from spatial neglect appears not to see or attend to half of the visual field, usually the left side, which is the opposite side of the damage. That is, they can see only what's on the right side of an object. Tests of spatial neglect include the following: cancellation task, where patients are asked to cross out all items, but they tend to cross out only those on one side, like what we see on figure A. Another is line bisection, where parents or patients are asked to mark the middle of the line, but they tend to mark the line to one side as we or as shown in figure B. And then there's also the copying task, where patients are asked to copy an image, but they tend to copy only one half of the image as seen in figure C. So, in all cases, patients can't detect what's on the neglected side. Things can be so severe that patients even shave only one side of their faces or eat half of the food on their plates. Patients with spatial neglect cannot visualize, imagine, or even describe the neglected side of a place. In one study, a patient with neglect was asked to imagine and describe a famous square in Milan. The person described the feature on the right side of the square. When asked to imagine and describe the square from the opposite side, the person again described the right side of the square, the opposite side from before. Clearly, someone with neglect does not have a problem with perception but with attention. Although patients with neglect seem unable to attend to one side, they are unconsciously aware of the neglected side. British psychologists John Marshall and Peter Halligan conducted a study in which patient PS was given two pictures. House A was normal line drawing. similar to what we have seen in figure C. House B was identical except that it has flames coming out from the upper window of the neglected side. PS was asked which house she would prefer. On 15 out of 17 trials, PS chose the one without flames but was unable to explain her preference. Now, patients with neglect can also identify symmetry in the neglected side. These findings suggest that they do have some unconscious awareness of the neglected side. In other words, some things can enter people's minds without attention and without conscious awareness. Now, attention deficit hyperactive disorder or ADHD is a common childhood psychological disorder. It occurs in 3 to 5% of Western children and is characterized by an inability to focus or maintain attention for a long time, leading to restlessness and potential aggression. Now, children with ADHD often interrupt others and are impatient. Cognitive tests of children with ADHD usually involves vigilance tests in which participants have to respond when they see a particular stimulus, for example, a square, among lots of other stimulus, for example, triangle. Each stimulus is presented one after another, with crucially the target stimulus presented very infrequently. Children with ADHD perform very bad at this type of task. They can easily name squares and triangles, however, showing that the disorder is one of sustaining attention. Another experiment, another experiment asks participants to respond with a button press when they see an X and a different key when they see an O. So children with ADHD perform well at this easy task. An instruction to stop the response when a sound is played at the same time as X or O occurs on a few trials. The stop signal paradigm. Children with ADHD are less likely to stop on these trials than other kids, showing that children with ADHD have problems with inhibiting their response too. One treatment for ADHD is the stimulant methylphenidate, which makes the brain more responsive. The idea is that the brain of children with ADHD or people with ADHD needs more stimulation to show the same activation as children without ADHD. Methylphenidate makes children with ADHD perform better at the stop signal experiment and makes them able to inhibit. In this video, we describe the key features of what attracts attention, what doesn't attract attention even when it probably should, and how attention helps you search for things. We also discussed how to control attention, the mechanics of involuntary attention, and some clinical disorders of attention. Once again, my name is Dex Kamitan and thank you for watching.